Yeah, so formula-wise, it's really not too crazy, but we talked about the physical and geometric relationships that are embedded in this. And it really just boils down to the idea that you have an equation, solve it. I think the inverse approach is probably the nicest way to go about doing it. I mean, as long as you can clearly identify what's what, the beta value, the beta matrix, is the basis for your vector space. Right? So once you have that, you're all set. The challenge, as you'll see on the actually before we get to markup change, we'll be doing change of basis. The challenge is going to be to come up with the change of basis matrix, which can be a little fun. But spoiler alert, it involves reduced row echelon form. So how bad could it be? Again, so x equals beta times x of beta. And again, we're looking for the coordinate vector relative to the given basis. All right, so x is in our system, x of beta is with the new basis. Okay, so if you were to actually change universes, so you go through a portal, you're in a new universe, if you were to go to whatever we get as a result for x of beta, that would bring you to the same location as 2, 3. But you might be standing at negative 150 comma 42. All right, so it's just completely different framework.
That would be always the formula x equals b.
Yep. So we have 2, 3. And we have our beta. 1, 2, negative 1, negative 1. Beta matrix is telling us where I and j are going. Instead of 1, 0, 0, 1, this is what the transformation is taking us to. All right, we're expecting another 2-unit matrix, which we can call, if you want to actually put it in vector form, you could designate it any way you want. You can call it x of beta 1, x of beta 2. I think it said matrix, I meant vector form. X of beta 1, x of beta 2. Or you could just use the simple notation of just the bracket x of beta, and then just let the chips fall where they may. All right. But you should at least have a sense of what you're on the lookout for in terms of a final answer. All right. So we know again that we don't have matrix division, but we do have the ability to multiply both sides by the inverse of a matrix. All right. Provided that that matrix is invertible, so just do a quick checkarooski on that and make sure that that's a thing. So diagonal down gives you a negative 1, diagonal up gives you a negative 2. Not going to give you a 0, that's all I care about. If you want to do it by hand, that's your business, I guess. So 1, 2, negative 1, negative 1, inverse, multiplied against the 2, 3. You know, sometimes you can get a little calculator fatigue, where it's just like, it's not hard, you just don't want to do it. So if that's the case, then feel free to, just crank it out by hand right quick. I went to the same one. So matrix A as an inverse multiplied by matrix B. So negative 8, 5. So if you played by their rules in their universe, where every step in the x direction is really going in the direction of vector 1, negative 1, every step in the y direction is going in the direction of 2, -1. Following their rules, when you got to their -8.5, you'd be at our 2.3. Right, but you know, calculation-wise, it's nothing too crazy, because really, when you think about it, what are you doing? You're taking the inverse of your transformation matrix and multiplying it by the given vector. So it's going to be the same operation. This operation, I'm just going to have, for C, I'm just going to have a different A and B. One, 2, 1, 1, 0, -1, 3, 8, 3. And so you get that. Well, I can just write that. So x of beta (1, -1, 1). All right, so again, in their universe, following their ijk values, going to their 1, -1, 1, you would arrive at our 0, 0, -2.